Welcome. So we have been talking about the Klein-Gordon field for a while now, and we have mentioned that it is its excitations that ends up producing particles, but we haven't really gone into the details, right? We haven't really seen how it actually happens mathematically. So that's what we're going to do in this video. I'm going to just let you know and basically make you understand exactly how the Klein-Gordon field actually describes particles. Okay, so to do that, let's just go back and recall some of the expressions that we have derived before. So here I have written down some of the expressions that we have derived previously and that we will now use to understand what the Klein-Gordon field describes. So the first expression here is simply an expression for the momentum that we found from the energy momentum tensor that we derived using the Noether's theorem. I did that in the previous video in the playlist. You can go and watch it there if you don't know where that expression came from. And these two expressions are just the field and the conjugate momentum, right? Field and conjugate momentum. And we're going to use them now to find this momentum expression. And why? Because, well, that momentum operator, when we let it act on the vacuum, is going to give us the particle that we want. So that's why we are interested in finding it, so that we can let it act on the vacuum, okay? So let's just plug this in to our expression. So we have minus the integral over all of space. And now we have pi, so that would be d3p 2 pi cubed. But notice we have minus I. So the minus will cancel out and we can leave the I outside. Then we have square root 1 over square root of 2, and we have square root of omega p. And then we have a p minus p dagger and e to the I px. Then we plug in not phi, but rather its space derivative, so the space derivative, but the only thing that depends on x here is this exponent, so the derivative is easy, it's IP. Here, P of course being a vector, right? Because this is basically 3 equations in one. That's why it's still got that vector form. Okay, so that means that in this expression, first of all, we need to make a distinction between the momentum in each expression because P and P prime are not necessarily the same, okay? At least for now. We don't know anything about it. So then we want this expression. So we have to multiply by IP. The p will remain inside of the integral, of course, but we can take the I outside, which will give us a factor of minus 1, right, when multiplied with the other one. Then we have this 1 over square root of 2 omega p. So the square root of 2 will just become 2, or 1/2, and the square root of omega p will just cancel out. Okay? And now we multiply by this expression, but all the p's have to be p prime. So p prime. And then we have, well, another 2 pi cubed. So this is now 2 pi to the 6th, by the way. And then we have p prime, a p prime plus a minus p prime dagger. And e to the I p prime x. But we can just put both of the exponents together, just add the exponents. So we have e to the I. This would be e to the I p plus p prime x. Okay, and now look at what we have here, because this is something that will happen very often in quantum field theory, so you should know what I'm doing now. In fact, we have already used it quite a few times before. So we know that the integral d3x over 2 pi cubed times e to the I p plus p prime x, this is simply the definition of the Dirac delta of p plus p prime. Okay, this is very, very common. When you are integrating over all of space, divided by 2 pi cubed, and then you also have the exponent of something, and sometimes you even have the exponent e to the 0, which is basically 1, and it doesn't even show up, and that's where you get the definition of the Dirac delta of 0. But this is something that happens very often, okay? So we can now plug that in. So basically we get rid of this, and also the exponent, and also of 3 of those 2 pi's. And then we have delta, actually I wanted to use black. So delta cubed p plus p prime. And what that means is that now in our integral, which is of course a sum of an infinite amount of terms, the only one that will not be 0 is the one when p prime is equal to minus p, okay? So that means that this delta will kill one of the integrals and turn every p prime into minus p. So this is now minus p. This p prime is now minus p. So this is minus p. And this here is going to be plus p. Okay, so now that we have dealt with that, we can go ahead and multiply through. So we have pi minus 1/2. We integrate over all of momentum space here, 2 pi cubed. And then we have, well, let's just shove the momentum to the front here. This is minus p. And then we have AP, A minus P, so AP, A minus P. Then we have, sorry, I wasn't supposed to close the parentheses there. So plus AP, AP dagger minus A minus P dagger, A minus P. And then we have the next one, which would be minus A minus P dagger, A P dagger. Okay, so with that, let's now multiply, actually separate some of our expressions first. So first of all, let's write this in the following way. So pi, this will be minus 1/2. I guess the minuses, you can just cancel them out, right? This and this, so you get just 1/2. Integral of d3p 2 pi cubed. And now I will only take those of these operators that the combination is odd, okay? And that's going to be AP, A minus P, and A minus P dagger, AP dagger. And I will show you why in just a moment. So I'm just separating this integral in a clever way for now. So d3p 2 pi cubed, and then p times, well, the other one. So AP, AP dagger minus A minus P dagger, and then A minus P. So let's begin by looking at the first term here, which I separated because it turns out that it is odd. So this thing here is odd with respect to P, to the momentum. But now that may not be obvious to you, so, and if it wasn't obvious to me when I saw it, so let me just show that to you. So this thing right here, let's just see what happens, right? What is an odd function? Just a quick reminder. So f of p, we say it is odd if it is the same as minus f of minus p. And if this integral here, if this expression here inside is odd, right, this here being our function of p in this case, if it is odd, then we are integrating over a symmetric interval, an odd function, which we know will be 0. So let's see if this function is indeed odd like I said it is. So to do that, let's see what f of minus p is. So f of minus p is minus p, a of minus p, a of p, minus a of p dagger, a of minus p dagger. Okay? But now keep in mind that the commutator between a minus p, ap, is the same as the commutator between AP dagger and A minus P dagger, right? Which is 0. So that means that you can simply rearrange them, right? Because again, what this means, for example, is A minus P, AP is the same as AP, A minus P. That's what we're saying. So that means that we can simply reverse the order here and go back to what we had before, right? Simply AP, A minus P, and here A minus P, AP. So what this thing here is exactly minus f of p, right? So that is exactly the condition for this function being odd. So that means we're integrating an odd function over an asymmetric interval. So this entire thing here is simply 0. Okay, so now this is the expression that we have. So maybe let's just write it like this. So this is our pi. So this is the expression that we now need to deal with. Maybe let's just take a moment to get rid of this so that it doesn't annoy us on our way forward. So this is now our expression. Well, we have actually dealt with a very similar case in the past. So what we'll do is simply multiply through by p. So we have 1/2 integral d3p 2 pi cubed. And now we have p, AP dagger, and then minus p, a minus p dagger, a minus p. And now we're going to do to only the second part of the integral, right? There are basically two different integrals, so you can change one independently of the other. We are going to say, let p go to minus p. This is the very common trick that we are using like literally all the time. So because again, we're integrating over all of space, it doesn't matter in which order we are doing it. So we can just change to minus p, it doesn't matter. So this is now positive then. This is now plus p, and this is now plus p as well. So we have p and p. Okay, so after doing this, I'm maybe going to use the same color here. It looks a bit weird. We can again factor out the momentum. So we can just factor it out, leave it somewhere over here. And now see what we have inside. So we have AP dagger, AP. So what we're going to do here is just like we did in a previous video, try to write this in terms of commutators. So since we have AP dagger, AP, we can try to write this somehow in terms of commutators. So for example, we can say AP dagger, we know that this thing minus AP dagger, AP, this is simply the commutator, right? AP dagger, and we know what its value is, right? This is going to be 2 pi cubed in our normalization, of course. In other normalizations, it may be a bit different. P, in this case, it would be P minus P, so that would simply be 0. Okay, so we want to construct then this commutator inside of this integral. So to do that, we simply subtract minus AP dagger AP, and we also add AP dagger AP. Okay, so by doing this, maybe let's change colors now. So we have our integral here, 2 pi cubed. So what do we have? So we have P times, and now we have AP dagger minus AP dagger AP. So first we have the commutator that we wanted, so AP dagger here. And then we have plus 2 times AP dagger AP. Okay, so what this means is that we have one of these terms. Now I'm going to just switch the order in which I write them. So we have the integral over all of momentum, 2 pi cubed, P times AP dagger AP. So this corresponds to that part, of course. And then we have plus this thing here. This, as I said, is simply 2 pi cubed. So 2 pi cubed and the delta function of 0. But that is, again, this infinite term that we will just call, this is a renormalization term. And, or rather, more than that, it is a term that appears because we are not using normal order in our product yet. And that is one that we can usually drop because it appears only, right? This additional term, that is this one, appears as a constant, and only because we have a lot of ambiguity in the way in which we have defined our product of operators. Okay, if that doesn't make sense, don't worry, because we will continue to go into that concept in the future. But what this basically means is that we are going to drop this part and simply keep this one. So this is the one that we will keep. So this is the momentum operator that we will be using. Okay, so now let's just quickly discuss what the meaning is. And basically we want to find these statistics here. So what we're going to do here is just keep in mind, we will have some state that we will label P, which will arise as the creation operator acting on the vacuum. Okay. Now this state P, how many particles does it have? Right? If we use the number operator, which again is simply A dagger A, if we let this operator act on the state, we will simply get 1 times the state. So there's only 1 particle here. Now, what is the energy of this state? We get that, of course, by letting the Hamiltonian act on the state. That's simply going to be some energy, P. And its momentum will come from the momentum operator acting on this state, which will be p time. Okay, so this is a bit confusing. So this is momentum operator. This is just going to be the momentum itself. And p is just the label here of the state. So a bit confusing maybe in the notation. Now from this, note of course, that if we take, for example, simply these two expressions here, we can just construct that the Hamiltonian minus the momentum operator here squared acting on p, right? Simply taking these two expressions squared and subtracting, we get that EP squared minus p squared acting on this state. And this thing right here is simply m squared p. And what we have here, right, this is simply what we have seen before. This is the Klein-Gordon equation for a single particle. So this is Klein-Gordon for a single particle. So what we saw at the beginning of the course for a single particle. Now, why is this relevant? Because this says that the particle that we create with our operator satisfies the Klein-Gordon equation for a single particle. Okay, so basically the thing that we create acts like a particle. That's the point. Whatever we are creating is acting like a single particle. Okay, and what happens now if we have multiple particle states, for example? If we have a state where we have n1 particles with momentum p1, and we have n2 particles with momentum p2, and we have n3 particles with momentum p3, and so on. Well, here notice that we really don't have any tools to differentiate, right? So all we can say is, oh, how many particles we have of a given momentum, but we don't really have any way to distinguish between one particle and another that are in the same state. So what I'm saying here is that the particles that we are describing using the Klein-Gordon field theory obey what we call Bose-Einstein statistics. So Bose-Einstein statistics. Hopefully you have heard that expression before. If not, it doesn't matter. Statistics. So what this means basically is that these particles are interchangeable, right? You can have a lot of them in the same state. You cannot distinguish one from the other. That's very, very, very important. Now, another thing that is going to be quite important is that we decide what the normalization of the vacuum is going to be, right? So we will just choose the normalization that the inner product of the vacuum with itself is going to be 1. So that's quite a logical way to do it. And we also need to define a normalization between two states, P and Q. So the most, I guess, logical one that we could come up with, which is this one, so d cubed P minus Q. This normalization would actually not be Lorentz invariant. So that's why, I mean, some books do use this, even though it's not Lorentz invariant, but the one that we will choose, it will be one that is Lorentz invariant. So we are going to choose that the expression P, right, this state P, is going to be square root of 2 EP times the creation operator acting on the vacuum. So a bit different from what we discussed previously when we were just talking about the statistics of the system. So using this expression, we can now write this inner product as 2EP times 2 pi cubed times the delta function. Okay, so this is the normalization that we will be using. Now, there will be some important normalization factors that we will use in other expressions. Some integrals will have a normalization factor as well, but we're going to discuss that as we get to those, because I think that just giving them out before we ever use them might be a little bit confusing. Okay, so now let's talk about the interpretation of our field acting on the vacuum. Okay, so that's something we would really like to know. So to do that, let's take the expression that we already know for the field and let it just act on the vacuum. Okay, so by letting this act on the vacuum, well, first of all, notice, of course, that the annihilation operator acting on the vacuum will give us 0. So the first part will give us 0. And then we have, well, integral d3p 2 pi cubed 1 over square root 2 omega p. And then we have, so a dagger minus p e to the I px acting on the vacuum. Well, here we can just do a little bit of a change. So let's go from p to minus p again. So p to minus p. Because we know what a dagger of p acting on this operator does. So we can just write this like this, but change the minus sign in here. And here we can just reverse the order real quick. So this will be e to the minus IPX, AP dagger acting on the vacuum. But what is AP dagger acting on the vacuum? So just a few moments ago, we defined that 2 times the energy of the particle, which by the way, at this point, we can just make our constants, or rather the energy have the same name. The variable of the energy have the same name, EP, which is what omega was standing for before. But before we didn't really have the interpretation. That's why we just kept it as omega for then. So this is the state P. So of course, we don't have this part just yet. So AP dagger acting on the vacuum is simply this state P divided by the square root of 2EP. So now we can just plug it in here. And by doing that, we will have the integral over all of momentum 2 pi cubed. And then we have 1 over 2EP, right? The square root is now squared, so it goes away. E to the minus IPX times now the momentum state P. And now notice too what we have here. So basically, this thing is a linear superposition of single particle states that have just a well-defined momentum. And this is almost the exact same expression that we found for the eigenstate of position x when we were dealing with non-relativistic quantum mechanics. And for that reason, what we will do is give this operator, right, this field acting on the vacuum, the same interpretation that we gave to this state back then, right? So what this means is that the operator phi of x will create a particle at position x. So this creates a particle at position x. Okay, so that is the meaning of our field as an operator. Okay, so that is the way in which you can interpret some of the things that we have found so far. So the important thing to note exactly is that phi creates particle at position x, okay? And so far, the Klein-Gordon field is describing Bose-Einstein statistics, okay? So particles are basically interchangeable and many of them can be in the same state. So that is what we found in this video. And we also, of course, found a very nice expression for the momentum operator, while also just getting a bit more acquainted with some of the algebra that we need to do when doing quantum field theory. So I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.